Boom. All right, so we are in the fourth video in our series on surds. In this video we're going to look at how we combine surds, right? And as you would see, following closely from the end of the last video, we're going to get into the whole issue of the similar surds, because the similar surds allow us very quickly to add and subtract surds. So for example, if I have let me say 2 root 3 plus 4 root 3, that is equal to 6 root 3, right? Because as I would have mentioned in the previous video, if I factorize this, I'll get root 3 into 2 plus 4, which is root 3 by 6, which is just 6 root 3. So in other words, if you have the same surd factor, if you have similar surds, then you can add similar surds by simply retaining the same surd factor and adding the coefficients, which is what we did here. 2 root 3 plus 4 root 3 is 2 plus 4 by the same root 3, which is 6 root 3. So you just add it. So in the same way that 2x plus 3x, 2x plus 4x is 6x. In the same way that 2y plus 4y is 6y. Then yes, 2 root 3 plus 4 root 3 is 6 root 3. And by the same token, you can apply the logic to subtraction as well. So if I have, let me say, 7 root 5 minus 2 root 5. Again, because we have the same surd factor, 7 minus 2, 7 root 5 minus 2 root 5 is simply 5 root 5, which we would get if we factorize, taking root 5 as the common factor, root 5 into 7 minus 2, which is root 5 into 5, which is 5 root 5. Yeah? So, in the same way that we were able to combine by addition, we will do the same thing using subtraction. So, in other words, the same surd factor, expressions having the same surd factor, allow us to effect a linear combination, which is to say, we could add and we could subtract. Alright? Now, if you have more than 2, you can do the same thing too. So, quick example. If we have 2 root 3 plus 4 root 3, now we say 2 root 3 plus 4 root 3 plus 7 root 3 minus 9 root 3 is equal to what? We just add them together. Yeah. 2 and 4 is 6, and 7 is 13 minus 9 is 4. That is 4 root 3. And if I have 7 root 5 minus 2 root 5, and let me say we add 6 root 5 minus 12 root 5. Right? Then 7 minus 2 is 5. 5 plus 6 is 11. And then 11 minus 12 is just simply equal to minus root 5. Right? So you have a negative quantity, minus root 5. No problem with that. The surd, let me make this absolutely clear. The surd is root 5. Root 5 alone, not minus root 5. So in other words, we know that the square root of a positive integer is plus or minus, right? So for example, we know that the square root of 36, we know that the square root of 36 is plus or minus 6. We know that the square root of 256 is plus or minus 16. right? However, when we're talking about surds, the only value that is covered by the square root sign is the positive value. So in other words, if we have to say the square root of, let me say, the square root of 37. Square root of 37 is the positive value, whatever that is, 6 point something. If we have to include, for any reason, the negative value of the square root of 37, what we'll write is this. We'll say plus or minus the square root of 37. Alright? So this is a surd. This is not a surd. Right? The surd only applies to the positive value. Be very clear on that. So if, as we have here, to deal with the negative value of the square root, we do that by putting a negative sign in front of the 5. So in other words, we know that the square root of 5 will give us two values, plus or minus 2.236 going down the road. So the root of 5 is plus or minus 2.236 going down the road. Yeah? However, for the purposes of surds, the surd representation is root 5, and that only covers the positive value, which is 2.236 going down the road. If for some reason we have to include minus 2.236 as part of our consideration, then instead of just putting root 5, what we will put is plus or minus the square root of 5. And once we do that, we're no longer talking about surds. That is just one little piece of information there. Very important. And that is why up to this point in all the videos in this series, everything that we did so far involved only positive quantities. Now suddenly, boom, you have a minus sign in front of a surd. Right? So this is the surd, the negative coefficient. Plus or minus the square root of 5 of root 5 is not a surd. However, if you have root 5 with a negative sign of it, you just have a surd with a negative coefficient, not a negative surd. So in other words, from a purely technical standpoint, the concept of a negative surd doesn't exist. However, you can have a positive surd, which is what a surd is, because a surd by definition is positive. You can have a surd with a negative coefficient, which if you want to be less than technical, you can refer to as a negative surd. But if you want to be purely technical, no. It is not a negative surd. It is a surd with a negative coefficient. Yeah? Be careful. Pay attention to your phrases and your language. Right. So we have seen that we can add or subtract similar surds because the similar surds have the same surd factor. Right? So if we have to add or subtract surds in addition to other things, we can do what we normally do in maths and bring the like terms together. And since the surds have the same surd factor, then they can be considered as like terms. So for example, let me do an example. So if I have to simplify the following. If I have to simplify, let me say 2 root 5 plus 7 minus 9 root 3 plus 8 minus 4 root 5 plus 11 plus 4 root 3. We have integers. You have surds where the common factor is root 5. and they have surds where the common factor is root 3. So if for any reason you have to simplify a situation where you have surds with different factors, then we bring the like terms together, and that simply means grouping the surds with the same factor together, and then you group the integers together, and then you drill down and you simplify. So if we have to do this, for example, we would get, let me start with the integers, right? You got 7, I'm putting everything in brackets there, 7 plus 8 plus 11, that's the integers, plus brackets 2 root 5 minus 4 root 5 plus let me say 4 root 3 minus 9 root 3. Yeah? I put the 4 in front of the 9 just for simplicity. And then we come again and we say 7 and 8 is 15 and 11 is 26. Plus, brackets again, 2 minus 4 is minus 2 root 5. 4 minus 9 is minus 5. Plus, minus 5 root 3. Which will give you, in the final analysis, you'll get 26 minus 2 root 5 minus 5 root 3. Alright? This, of course, is a compound surd because you have an integer in a linear combination with two other surds. You have a surd with in root 5 and you have a surd in root 3. Yeah? So if we have to add or subtract two or more surds, then the surd factor has to be the same. Let me say it again. If we have to add or subtract two or more surds, then the surd factor has to be the same. However, in the case of multiplication, it is not necessary for the surd factor to be the same. You could have surd factors, different surd factors coming together to multiply. Examples again. So let us use the same surd factors that we have here. We have 2 root 3 and we have 2 root 5 and 4 root 3 and 7 root 3 and all of that. Right? So let me use the factors root 5 and root 3 to demonstrate that you don't have to have the same roots, the same surd factor. So if I have two surds, if I have root 3 and I have root 5, if I have to add those two, there's nothing else I could do beyond that, because the surd factors are different. If I have to say root 3 minus root 5, I can't go further than that in terms of simplifying, because the surd factors are different. In other words, if you want to use simple basic language, the integer under the square root sign is different. So if the integer under the square root sign is different, the integers, under the square root sign are different, then you cannot add or subtract. If you have to add or subtract, the integers under the square root sign have to be the same. However, I can in fact do this. I can multiply root 3 by root 5, even though the surd factors, the integers under the square root sign are different. And root 3 by root 5, remember we made reference to this law earlier on in the Surds videos. Root 3 by root 5 is simply the root of 3 by 5 which is equal to the root of 15. We could do that. And again, the reason why we could do that is because, and I'm writing the law in reverse now. If I have a to the power of n by b to the power of n, that is equal to ab to the power of n. Of course, if we make n equal to a half, a to the power of half by b to the power of a half is equal to ab to the power of a half. And of course, if we use the notation of the square root sign, what you will have is that root a multiplied by root b is equal to the root of a b. So we applied that principle there, and that allows us to multiply two surds. It is as simple as that. So we could do some quick examples just to drive home the points. Yeah? So if I have, let me say, root 2 by root 3, that is the root of 2 by 3, that is root 6. If I have root of 17 by the root of 5, 17 by 5 is the root of 85. If I have the root of 21 multiplied by root 3, that is the root of 63. Now, if we multiply into surds where the surd factor is the same, what we'll actually end up with is an integer. Simple example. Root 5 by root 5 is 5. We know that, right? Or maybe we didn't know that. That's all right, no problem. Root 5 by root 5 is root 5. 2 root 5 multiplied by root 5. Root 5 by root 5 is 5 by 2 is 10. 3 root 7 multiplied by 4 root 7 is equal to root 7 by root 7 is 7. 3 by 4 is 12, so that will be 12 multiplied by 7, which will be 84. Right? Etc., etc., etc. So anytime you have the same surd factor in a multiplication, you will end up with an integer. Of course, we're talking about only if you have two numbers that you're multiplying, because if you're multiplying two roots and if you're multiplying the same roots by itself, then you will get the square root. So root 7 by root 7 is 7, root 5 by root 5 is 5, etc., etc. Alright? I want to apply this to this here now. Right, let me go back a little bit now. So if I have, because the same principle applies, if I have 2 root 2 by root 3, root 2 by root 3 is root 6 by 2 is 2 root 6. If I have 4 root 5 multiplied by 6 root 5, no, not root 5, 6 root 7, random roots, right? Root 5 by root 7 is root 35, and 4 by 6 is 24. So you get 24 root 35. Right? I don't think you could get simpler than root 35. Right? So 24 root 35, yeah. Right? And of course, as we saw here, if the surd factor is the same, what you will in fact end up with is an integer. So what about, let me say we're multiplying three numbers, three surds by each other. Let me make it a little more complicated, just to drive home the point, so that you will be in no doubt at all as to what in fact we do in here. So let me start with these guys here. Let me start with the same surd factor. If I have root 5 multiplied by root 5 multiplied by root 5, because it is a root and I'm multiplying 3 times, root 5 by root 5 is 5, and then 5 by root 5 will just simply be 5 root 5. Alright, that's all it is, you know. 5 root 5. How about our friends here? If we have 2 root 5 multiplied by root 5, and then we say we're multiplying that by 3 root 5. Right? 3 by 2 is 6, so we can multiply the whole numbers. That'll be 6. Root 5 by root 5 is 5. 6 multiplied by 5. And then you have another root 5 here. That will be multiplied by root 5. So that will end up with 30 root 5. Root 5 by root 5 is 5. 5 by 2 is 10. 10 by 3 is 30. 30 by root 5 is 30 root 5. Right? Let me just finish it there. 3 root 7 by 4 root 7. 3 root 7 multiplied by 4 root 7 multiplied by, let me say, 2 root 7. That will be what? 3 by 4 is 12 by 2 is 24. Right? Root 7 by root 7 is 7. So 24 by 7 is how much? 96 by 3 is 288. 96 by 3 is 288. 288 by 2 is 576. I like to challenge myself. I like to challenge myself a little bit. Let me see. 576. Let me double check it. 3 root 7 by 4 root 7. 3 by 4 is 12. 7 by 7 is 84. Sorry. 3 by 4 is 12. Root 7 by root 7 is 7. 12 by 7 is 84. What craziness I was doing just now? What madness I was doing just now? What I do just now? I said 3 by 4 is 12 by 2 is 24. Right? 24 by 7 is, we said that was 24 by 4 is 96. Oh, 96 plus 72 is 24 by 3. 96 plus 72 is 9716, and that's 68. What did I do? I moved from 96 to 288 or something like that. Oh, I multiplied 96 by 3. That's a mistake I make. Madness. Right? So 3 by 4 is 12. By 2 is 24. 24 by 7 is 168. You get 168 root 7. Alright? That is one way of working it. 3 by 4 is 12. Root 7 by root 7 is 7. 12 by 7 is 84. 84 by 2 is 168. 168 root 7. Nice surd, man. Alright? Right. So you see how the multiplication enters the picture when we have different surd factors and when we have the same surd factors. No, well, we ain't do the different surd factors yet. Well, let me do the different surd factors now. Let me make it nice like Spice Man. Excuse me. So if we have 2 root 3 multiplied by 4 root 4 multiplied by 6 root 7. Let me make life nice now, man. 2 by 4 is 8 by 6 is 56. So that's 56 multiplied by root 4 by root 3 is root 12. Root 12 by root 7 is root 84. 56 by root 84. So you get 56 root 84. Now, if you look at root 84, you will see 4 root 4. Listen, anyway, let me finish it. Because I could use this as an opportunity to demonstrate the simplification. Root 84. 84 is 4 by 21. Right? So this is 56 by the root of 21 by 4, which is 56 by root 21 by root 4. Root 4 is 2. 56 by 2 is 56 by 2 is 112. 112 root 21. Wee papa. Right? Now the reason why I got root 84 is here is because I had 4 root 4, which doesn't make sense. 4 root 4 don't make sense if we talk in surds. Right? So let me do another example just to demonstrate that we can in fact multiply surds with different surd factors. Right? Sometimes when we do need random examples, we just come up with some crazy stuff. But all of that is what does make the maths nice. So let me go again. Let us say you have 5 root 2 multiplied by 4 root 3 multiplied by, let me say, 7 root 5. That is equal to 5 by 4 is 20 by 7 is 140 multiplied by root 2 by root 3 is root 6. Root 6 by root 5 is root 30. Alright? So that will be 140 root 30. I don't think root 30 could get simpler than that. 140 root 30. 30 is 5 by 6. Yeah, 140 root 30. That is as simple as I could get. So, if you have the same surd factor, if you're just multiplying 2 surds, you'll get an integer. If you're multiplying 3, you'll get a surd in the same factor. If you're multiplying 4, you'll get back an integer because you'll have a root multiply 4 times. So, simple example. If we have 2 root 3 multiplied by 3 root 3 multiplied by 7 root 3 multiplied by 9 root 3, right? The numbers will end up being kind of big. So what you'll have will be 2 by 3 is 6, by 7 is 42, by 9 is 420 minus 42 is 378. 420 minus 22 equal 498. No, I minus 22. 420 minus 42 is 370. Yes. 42 by 9 is 378. Beautiful. So what you'll end up with will be 378. Root 3 by root 3 is 3. Root 3 by root 3 is also 3. 3 by 3 is 9. So you'll end up with 378 by 9. Which is equal to what? 378 by 9 equal 3,402. Right, etc., etc. So in other words, once you understand the basics of combining surds, whether you're doing it by addition or subtraction, which would be a linear combinations, or whether you're doing it by multiplication, yeah, no problem. You don't have a problem. You just take your time and you do your arithmetic and you go on. So I will end this video here. Right, I'm trying my best not to have the videos longer than I need to have them once I have the ability to stop the video. There will be times when I'll have long videos, 45 minutes, and in some cases over an hour. But most of the videos will be a lot shorter than that. We break it up in small bite-sized chunks so that we could take our time and digest it piece by piece. So I'm going to leave the issue of division of surds for the next video. So stay tuned and look out.